Increasing of the switching frequency of the power electronics converter is always be helpful because increasing of the switching frequency increase the power density of the converter and reduce the weight. Here the shown structure is of the buck converter, the basic buck converter. Here the S1 prime is representing the switch S1 and T4 configuration because the as I mentioned in the LT spice, if you want to create the ideal device, then you have to encounter few points. Those few points I have already mentioned in my other lectures. So in today's, what is the problem if we are increasing the switching frequency? Those things we will discuss. The losses including with the switching extent. So whenever you are turning on the device, whenever you are turning off the device, the overlapping period of the voltage and current will introduce the power loss. What is that? Ideally, here the voltage, suppose this is the time and this is the voltage and current axis. Here you have turned on the device, then the voltage will drop linearly and the current through the device, let's say this voltage and current of the device switch S1 prime. Now the switch S1 prime, the current through the switch S1 prime is going to linearly. Those things we have assumed is a linear shape because we don't know how the practical device will behave at the time of switching instant. Let's say at the time of turn on and at the time of turn off. So for now, we can say here the power loss phenomena is triangular in nature. This is the switching power loss. Here, few results where switch S1 prime is replaced from the MOSFET, then how the shape will introduce. Here, the first one result is a gate to source voltage, what volt pulse, what gate pulse we are applying. And here, what is the power loss through the device? This is the power loss at the time of switching instant. Here we can easily see that here the spikes is coming at the time of turning on of the device, at the time of turning off the device. When the turning on of the device is happening, then we can see here the power loss phenomena is going up to 22 watt. But at the time of at the time of turning off the device, here we can see the power loss phenomena will go 10 watt. And this shape is different. This is not the exactly triangular. Here we are trying to transfer of the around 7 to 8 watt of the power, where we are getting 2% loss of efficiency, which means around 98% of the efficiency we are getting. Why this loss we should be keep here? Why is it any solution? We can solve it through that 2% of the losses. Here, yes, the answer is yes. We can use the soft switching soft switching technique that can avoid this 2% of the efficiency, and we can achieve around 99% of the efficiency if we are considering the only device losses. Here the soft switching techniques is divided between is classified between multiple types of resonant converters. Here the first thing we will discuss in today's lecture, that is the resonant switch converter, where the ZCS is one type. I am Rajat Kumar Shukla, and today I am going to present the zero current switching technique for the buck converter. Basic idea of the zero current switching, what is that? So let's draw the buck converter. Here this is the main switch S1 prime, and this is the VDC, and this is the diode D, and this is the output current. Here basically this phenomena is nothing but, this current source is nothing but, this is the inductance, capacitor and resistor. Because of this inductance is in series, that's why we can replace it. If let's say if this inductance value is very high enough, in that way load side branch, I mean this equivalent branch, we can be replaced with the current source. If this L is high, then we can replace it by the current source. So for now, for the understanding the basic idea of the zero current switching, I am just drawing this circuit to this circuit. The basic is the zero current switching is that only at the time of turn on and at the time of turn off, the switch current should be zero. How it will possible? Let's say if you are turning on the device, then the current should be drawn by the other side, by the other element. What is that element? That doesn't matter. Let's say if I am turning on the device, let's say this is the gate to source voltage prime. Here in this instant, there are the current will be drawing from the diode D. So this one it was turned on. When this switch is turning on, so our intention is to this load current, whatever the current is flowing through that should be not directly by the it should not be directly through by this switch S1 prime. It should be drawn by the other one, or it should be limited. So what we can do here, we can use one inductor. So let's say let me redraw the circuit. So one inductor here, so this inductor will limit the current, whatever the current is going through that. So let's say this is the current of this inductor. This name is IL, so I am taking is IL, which is nothing but this is the current of drain to source of the S1 prime. So here the current, if let's say previously this diode was turned on, the equivalent diagram you can see here, this would be kind of in this nature. So here the current through the IL or switch S1 prime, here the whatever the voltage is appearing here, that is the 0. So here the constant DC voltage is applying, which means the current is flowing through that is not exactly equal to I naught, but exactly equal to the current shape, whatever the current shape is happening here. So as we know that inductor is opposed the sudden change of current. So previously here in this instant the current was 0, so the inductor will oppose the sudden change of current. So it will not go through directly, but it will go through the linear shape smoothly. So it will rise up to whatever the current, whatever the current, let's say this current is I naught. Why this current I naught? We will see further now, but for now we are assuming that it is a current of the I naught. So this is called the ZCS turn on, because the current is very low in nature, very small in nature. If this current is very if the switch device current is trying to touch directly this I naught, then that would be called the hard turn on the device. Let's say if I want to turn on the device at the zero current switch, at the zero current, then what thing I have to encounter? The encounter thing is before turn off the device, before turn off this switch S1 prime, I have to put the this is my responsibility to that this current, this IR inductor current, that should be going to the 0 completely. I have to introduce the another branch of the current that will be carrying the load current, when I naught will be carrying by the device PDC. Here we have to introduce some branch. That branch can be inductor or capacitor. So that cannot be inductor because there are some reason. What is that reason? We will discuss later on. But for now, we will assume this is the capacitor. That capacitor will help to take the current of this inductor current to commute to this inductor current. Which means before turning off the device, before applying the negative pulse or zero pulse of the device here, switch S1 prime, inductor current automatically becomes the 0, and here the current, the load current will be care will be carrying by the capacitor C. So in this way the current I naught will be here at this pulse, and here we will be turning off the device, and we can see here at the starting of the current, at the starting of the switch, the current is limited by the inductor L, and here automatically the switch current is turned off. Not automatically, actually this is that current is carrying by the capacitor C. So this is called the ZCS turn off. So this is the basic principle of the zero current switching. So let's do it by the mathematical analysis. So here this is, as we know, this is a switch S1 prime, and we are considering that switch S1 prime is nothing but it is a SCR circuit, and this is our capacitor, and here the load, here this is the freewheeling diode, and this is our load current, and this is the source voltage Vs. Here this circuit will form the zero current switching transition or soft switching. So this is the ZCS circuit. This, please ensure that any soft switching circuit should be lossless, which means that should not be contain any lossy component like a resistive network, but that can have the any devices kind of diode, kind of MOSFET that can have. But usually we can prefer the diode but not other MOSFET. Here the switch L and C is named in this way. Suppose here I am turning on the device. Before that, here this is the VGS of S1 prime, and here this is the inductor current IL, and here this is the capacitor voltage. Now here I have turned on the device. So what will happen? The initially with, let's say this is the t equal to 0, then what will happen? The current, the switch S1 was opened, and the inductor will be like as a open circuit, and the current will be carrying by the I naught. So here I have just turned on the device, so what will happen? It will form some circuit that will be like this. So here you can see that VL, let's say plus minus, and this is showing the IL, then it will draw the VL is equal to LdI by dt, which means the current I of t shape is nothing, it's Vs divided by L in terms of time. But the question is how far it will carry the current IL. So the answer is I naught. But why? Because let's say, just assume that if this current is becomes I naught, then the current is open circuited. So you can see here the diode also coming like as a ZCS operation, which means I'm saying the inductor current is becomes the load current. So all current here is carrying by the inductor. After that, once it is reached inductor current, the capacitor coming into the action like this. Here the circuit form like here the initial condition was I naught, and here the capacitor becomes the action. Here one of the noticeable point that here let's say time is t1, where t1 time is defined, the switch current becomes the load current. Then this I naught current will increase linearly or not, that depends on this circuit condition. Let's say this is the mode 1 and this is the mode 2. So this is the equivalent diagram mode 1, and this is the equivalent diagram mode 2. Here you can say that the equivalent circuit diagram, or you can say here the inductor current wave shape becomes like in this fashion, where Vs divided by Z naught divided by sine omega naught into t minus t1, where omega naught is a resonant frequency and Z naught is the characteristic impedance. Or you can say here Z naught is square root of L divided by C, and omega naught is equal to 1 upon square root of L into C. It should be careful about that. Whatever the switching frequency you are using, that omega naught, that should be higher than from the switching frequency whatever you are using. Let's say if you are using the 100 kilohertz, then it should be in megahertz. Otherwise you may face problem. Here the Vc of t is should be in the shape of 1 minus cosine of omega naught t minus t1, which means here the current is coming like a sinusoidal in fashion, and here the capacitor voltage will draw some value. Here we can see here this is capacitor voltage will be higher at the pi by 2, right? Here the capacitor voltage it becomes is a Vs, and here the capacitor voltage becomes 2 times of Vs. After that, here capacitor already charged. Now in this region, suppose this is the mode 2 and this is the mode 1, then here in this region this is the time t1 and this is the time not t2, but so here the capacitor voltage becomes the 2 times of Vs. Now the thing is, in mode 3 what will happen? Inductor current already comes again the I0 and capacitor voltage already charged fully. Here the current, the inductor current, whatever the switch carrying the current is less than the I0. Question is, if you apply the KCL law here, you will get IL already less than I0, which means suppose it is carrying the 5 amperes of current and it was carrying more than 5 ampere, which means this inductor current can carry the 5 ampere of current. But if this is carrying the 4 ampere of current, then the 1 ampere current, which one is carrying? The answer is capacitor. So if the IL is less than I0, which is happening in the case of mode 3, then the circuit becomes like remains same like as a mode 2. So here we can say this is a mode 1 till t1, but if we say this is a t1 prime, so after the t1 prime till the till the switch current becomes 0, it will be follow the sinusoidal shape. So here the sinusoidal shape is starting at this point, and here this shape, this sinusoidal shape will be carrying, and it will be carrying till this negative point, because the capacitor current is carrying the I0 current, or you can say here the capacitor is trying to carrying the I0 current. So let's say this is carrying the 5 ampere of current, and this inductor current is carrying 4 ampere of current. Then this capacitor will provide the 1 ampere current. Here one of the noticeable point is that in mode 2 this capacitor like in a charging in nature, but here the capacitor is discharging in nature. That's why here the capacitor will draw some capacitor voltage value, because this is at the t1 prime instant capacitor has started the discharging scenario. Till the capacitor will discharge, not till the discharge, which means the capacitor is started to discharge, the inductor current, the current which is carrying the switch, that will show some some portion of the zero current. This time is very small, but you can say this time will be taken by the capacitor to discharge some energy. Now, in this is the mode 2 prime. So here, this instant is called mode 1, and this instant is called mode 1, mode 2, and this instant is called mode 2 prime. Here, this is the time t2 and this is the time t1. So after this t2 time, what will be happening? After this t2 time, it will take some time. But here, I have not mentioned that what is the happening with the gate to source voltage. Here already the switch has turned on. Let's say I have turned off switch here at this instant. Then what will happen? The thing is, capacitor has already charged. Inductor has no charge. Can inductor carry the negative current after this T2 time? That is the question mark. So the answer is it depends on the switch property, which means if after this point inductor current is not carrying the negative current at this region, which means the current was carrying in the forward direction, let's say in the 4 ampere direction. Let me draw the circuit in the next page. So our question was, at the time T2 at mode 3, what will happen? Can the inductor current in reverse polarity will observe or not? Which means can inductor carry that negative current? Here, this inductor I am talking about. So it depends on the switch nature. I have mentioned we are assuming this switch is SCR switch. SCR switch, which means it's shown like as a switch polarity, like a diode polarity, like anode and cathode, and it will draw some cathode circuit here. There is some gate circuit here. This is a semi-controlled switch. So this is the unidirectional in nature. It cannot draw the negative current. That's why this inductor current cannot go in the negative direction. Let's say if this switch can be a bidirectional like a MOSFET, then the question is, can the inductor current after this T2 can be a negative? So answer is yes, because the bidirectional switch can carry the current in the forward direction as well as in the negative direction. That's why if you are using here the MOSFET, then the current can be negative. So please be careful about this sign convention. So let's again take a topic. Here after this T2, current becomes 0 and it cannot go through the negative direction. So here the question is how this capacitor voltage will dissipate because there is no resistive load. So after this T2, the mode 3 will draw like in this circuit. Here the rest of the part in this direction is act like as a open circuited because there the current is like as a 0. So here the all current will be carrying by the capacitor. Which current? Load current. So the capacitor will draw the I0 current in the discharging fashion. So here still the capacitor is discharging in nature. So here in this mode 3, what will happening? Capacitor will be dissipating some energy to the load, which means here the one observable point, that is when the inductor will be having some energy here that will be dissipating through the capacitor also, and whatever the energy stored by the capacitor, that capacitor also giving the energy to the load. So no energy is destroyed. We are not interested on the dissipative circuit. We are always be interested on the non-dissipative circuit. So here LC is drawing non-dissipative circuit. Let's say this is a time T3. What will be happening after that? After T3 is, let's say this is the zone of the mode 4. So here in the mode 4, what will be happening? That is the question mark. So the answer is very simple, that current will be carrying by the freewheeling diode. Sorry if it is not showing here then. So that current, that I0 current will be carrying to the diode D here. So after this mode 4, let's say till the time period, total time period T. So here after that, this is the time period. After this time period, the again next cycle will repeat. So the same step will be happening for the each time period. I hope you understand. But if you are not understanding, let me derive again. So here in mode 1, the shape of the inductor is nothing but it depends on the inductor and time period t. At the time period t1, t is equal to t1, what will happen? The IL becomes the I0 and Vs becomes the t1 divided by n. What would be the capacitor voltage? Capacitor voltage becomes the 0. In mode 2, what will be happening? The happening thing was inductor current becomes equal to sinusoidal in fashion, which means Vs divided by Z0 into sine of omega naught t minus t1, and Vc will draw some sinusoidal fashion like this, 1 minus cos omega naught t minus t1. Here in mode 3 or mode 2 prime, here remember thing is mode 2 prime will draw the same current, so we can take it as this two equation, this remains same for the mode 2 also. So for what will be happen with the mode 3? In mode 3, IL becomes the 0. Vc will draw the I0 divided by CR T2 minus T1 plus Vc of T2. If you are unable to understand this equation, how it is coming, how we will derive, because these are the just the maths. So you can see the Daniel W. Hart book or Ned Mohan book for the power electronics converter. This equation have very well explained there, especially in Daniel W. Hart. I'm just summarizing the mathematical equation for this one. How we will calculate the output voltage? So we can use this concept that whatever the energy transfer by the load, by the source, that should be received energy by the load. So the energy transferred by the source is nothing but energy transferred to the inductor L. Received energy is nothing but I naught into V naught. Or you can say, sorry, not energy, but in terms of power, it should be I naught into V naught. But to take the input power, it should be input voltage, which is the constant, as we know that. So the what the inductor current is taking in terms of 0 to t. So here in partition inductor current, we can say that part is from 0 to t1 plus t1 to t2 plus t2 to t3 plus rest of the inductor current is 0. So if you integrate that, then and equate this term to this term, you will get the output voltage is nothing but it depends on the Vs into switching frequency T1 by 2 plus T2 minus T1 plus T3 minus T2. Why I am doing that? Because the output voltage here, it will show it depends on the switching frequency. If you are using the LC ZCS circuit with your buck converter, in that case the output voltage is not only depends on the D, but it is also depends on the frequency. But what is the big deal? The big deal is this switching instant. This switching instant, it depends on the load current I naught. If you expand this T3 minus T2, you can see here that Vc depends on I naught. Here again the inductor current, it depends on the Vs. Here again, here the T1 is depends on the I naught. So T1 is depends on the I naught. Here the T3, it depends on the I naught. So that these time instants are depends on the load. So this ZCS circuit have one of the drawback, that is these are the load dependent circuits, have the load dependent circuits solve some problem. and this inductor have 30 microhenry and zero point 0.1 microfarad capacitor. How I have decided this L and C value, that is the question mark again, but we will discuss it later. For now, if this have the switching frequency component of the 100 kilohertz, then the first question is what is the peak current will be achieved by the switch S1 prime. This current, this amount of current should be carry the this switch S1 prime should be carry the I naught current, but these are the extra current will be carrying by the switch S1 prime. This is the amount of peak value. So this is nothing but this extra current peak value is Vs divided by Z naught from the mode 2 equation. We can see here the inductor current Vs divided by Z naught sine omega naught t minus t1. Here the sinusoidal function will be peaked at the 90 degree. So Vs divided by Z naught is carrying the extra current. So here we can see the peak current is nothing but I naught into Vs divided by Z naught. So what would be the answer? This is the 1 ampere plus source voltage at 12 volt. Z naught is square root of L, which means 10 microhenry divided by 0.1 microfarad. We can calculate it. Now the next question is what would be the capacitor peak voltage will achieve by this circuit. So here let me draw this circuit. Let me go back to this waveform configuration. Here we can see that at this mode 2 prime, the capacitor voltage becomes the twice 2 Vs. So here the answer is very straightforward that it would becomes 2 Vs. So 2 multiplied 12 is nothing but 24 volt will be carrying. So capacitor you have to create of the double of the supply voltage, which means if you are increasing if you are using this circuit for the higher input voltage rating, then capacitor voltage value should be drawn at the higher capacitor voltage, which will increase the size of the capacitor. But in terms of if you compare the switching frequency, then this capacitor size always be lesser. Anyway, now the third question is what is the switching frequency we have to achieve if the capacitor if the output voltage will be drawing the 6 volt and instead of V0 previously was 7 volt, which means in this case the V0 was drawing the 7 volt. Suppose you have to maintain the load is constant. Load is constant, which means load current is constant. Then I have already shown that V0 is proportional to the Vs into switching frequency. If the load current is constant, then this term was constant, which means I am talking about this equation. These are the equation of the output voltage, and this term are highly depends on the load only and the input voltage and the inductance capacitor also. So here the switching frequency you can see the that is depends on the V0 prime divided by Vs prime multiply V0 divided by Vs, where the prime terms is showing the new values. So we can easily calculate by putting these values, because the previous switching frequency that mentioned 100 kilohertz put voltage is actually equal, so it is cancelled out. So V0 prime divided by V0, then switching new switching frequency you will get from this equation, which is nothing but equal to 85 kilohertz something. This is approximately value. Now the next question, if it's coming, what would be the maximum frequency we can apply for this circuit? So I have not mentioned here, that is the if what will happen if this T3 is becomes equal to this T, which means if This is the capacitor charging and discharging phenomena, whatever that is happening here. If it is equal, the last part, the age of this part, this T3 becomes the equal to T, or if it is greater than T, then what will happen? Then the answer is very simple. This T3 should be less than T or equal to T. If this T3 greater than T, this is the highly undesirable thing, because ZCS cannot be achieved at this condition. Why? You have to check it. So the maximum frequency will achieve by this time period this time T3. Always remember, T3 is depends on the L and C. So you cannot put maximum frequency. To achieve the maximum frequency, 1 upon T should be there. T is varying in nature because that is in our hand, but T3 is not in our hand. It is highly depends on the L and C. That is the reason I have put T3 in denominator. So this maximum switching frequency is nothing but equal to 6.8 micro. This is the time period of the maximum at the case of maximum switching frequency, it would be 6.8 microsecond. Then you have to just inverse it, 1 upon 6.8 microsecond. Then it would becomes the maximum switching frequency. Previous question was how we have used 10 microhenry and 0.1 microfarad. Then the first constraint to use ZCS circuit, the buck converter, the first thing, T3 should be less than the time period T. The second point is depends in your hand what is the IL peak current, because it is also decide, this is also decide the switch, the current stress on the device. So this is nothing but I naught plus Vs divided by Z naught. So how much this peak current you have to maintain, that depends on in your hand. So by using these two constraint, you can use the L and C circuit. This is a very obvious thing. If you are choosing the higher L, which means less switch current stress you will achieve. Increasing the higher L, then C value, you have to choose the lesser C value. That is, these are the very obvious things. But is it very straightforward or not? That you have to care about it. SPICE simulation results are here, where the switch S1 prime and inductor I have taken 10 microhenry only, and the ZCS circuit I have chosen the 0.1 microfarad only. And here this is the freewheeling diode, and this is nothing but this is the 1 ampere load current, and here the 12 volt input voltage. Here the shown red shape, this current is nothing but inductor current, and here this shape is showing the capacitor voltage in this way, in this direction, and this is the gate voltage of the device S1 prime. Here you can see that if the S1 prime, whenever it is turning on, here the current is starting smoothly. Sorry, let me change the color. The shape is starting smoothly, which means this is the ZCS turn on. So here let me write it, ZCS turn on. Now before the device has turned off, here device is turning off, right? So here the current through the inductor is 0. Here you can see that here is very small spike is there. That is for the different reason. That is not because of actual one. So here ultimately what I'm trying to say here, when you are giving the pulses for the turning off, before turning off the device, the current is automatically current is not in the device, but that is with the capacitor only. So that is the reason here you can see this is the ZCS turn off. I hope you understand that whenever the starting of the device, ZCS turn on, how the ZCS turn on is happening, how the ZCS turn off is happening with the device. Here the one of the remember thing is if S1 prime I have taken the SCR, then this circuit, I mean these results are valid and this analysis are valid. But the question is, if you are using the device like as a MOSFET, then what will happen? Like as a NMOS, PMOS, then our answer would be valid or not? That is a question mark. So that you have to take care about it, that the current would be go in the negative direction or not. It depends on the what type of device S1 prime you are using. So I hope you understand all the analysis what we have done today. If you have any doubt, any clarification you want, you can comment on the YouTube. Otherwise, you can go through this mail ID and you can mail us. Meanwhile, if you are trying this circuit in your LT Spice and you want to know more about it, or you want the answer what will happen with the zero voltage switching, then keep watching. Thank you.